Thank you very much for your kind introduction. And thank you to Susanna and everybody at MLT for giving me the opportunity to present our work surrounding quantum computing here in KPMG Ignition Tokyo. So before I go into the details about my work surrounding the quantum computer, I thought that I would introduce our organization a little bit. So KPMG Ignition Centers are located all around the world. Currently, there are about 25 locations globally. And our mission is to create business solutions that will help our clients navigate through complex and dynamic business ecosystems of today. And we aim to provide insights and unique values to our clients. KPMG Ignition Tokyo was established last year, and our objective is to support the digital transformation of KPMG Japan and our clients. And we aim to transform the synergy between our professional insights in audit, tax, and advisory and the latest digital technologies into concrete business values. And we provide a digital technology platform that are shared by our clients, and we act as a technological hub for KPMG Japan. So here in the figure, I illustrate our services provided by our organization. So we build everything on the foundation, technology foundation, be it the cloud, AI, and big data. And on top of that foundation, we build a technology platform, be it the secure computing platform or blockchain platform or classical quantum computing platform and so on. And then using the components within this technology platform and using the domain knowledge, we create the business platform, for example, to increase traceability, or even allows us to share the knowledge amongst the clients, or even to determine or to find anomaly, to make an anomaly detection engine. And then on top of that, we'll build an application layer that interacts with our clients. So there are 6 areas of technology focus areas at KIT, and we build everything on the foundation, once again, on the cloud, DevOps, and security. And one of our pillars is secure computing, and this is a technology that enables secure recording and near real-time sharing of highly confidential information. Knowledge processing, here we extract or recognize information from unstructured data, such as images, text, and speech. And using that type of data, we derive semantic values. Intelligent agent, this is a human-like agent, be it a chatbot or virtual avatar and so on, that enable natural conversation with humans in specific field. Scientific visualization is a visual, auditory, and tactile feedback technology for humans, for example, BI tools. Smart transaction, and this will be the focus of today's talk. And this is the detection of anomalies from transactions and other types of data. And here we hope to go beyond the current capabilities of human auditors. And finally, the edge computing. This is a real-time data capture technology centered on IoT, blockchain, and next-generation computing technologies. So there are 3 components to our organization, and they are Insight Center, Innovation Lab, Lighthouse. And using these types of components, we aim to achieve a new model as a professional firm. So in the Insight Center, we provide visualization of interactive data utilizing the latest 3D data visualization technology. In an innovation lab, this is a space for creative discussions to induce open innovation, and we assist our clients in creating solutions such as strategy formulation, solution proposals, design thinking, workshop, research, and concept planning. And finally, the Lighthouse. Here we gather the technology experts in one space for the research and development of solutions utilizing cutting-edge technologies. And this Lighthouse is a global initiative. And then in a global Lighthouse is a team of data and AI and emerging technology experts. And we currently reside in about 32 member firms globally. And we initiate activities or initiatives such as emerging technology community, where we focus on Horizon 2 and 3 technologies. And we meet on a regular basis to talk about various updates from various regions, or if there are client engagements and so on. So the focus area of this particular initiative is on the quantum computing, augmented reality, virtual reality, and edge AI, and so on. We also recently initiated a network called the Capability Network. Here we discuss about the Horizon 1 and Horizon 2 technologies. So we share things like go-to-market material, success stories through client engagements and things like this. And here our focus is on the forecasting and anomaly detection, computer vision and language model, and cloud transformation. So KIT is an imagination-driven organization, and we welcome world-class experts in each technology areas, regardless of nationality, race, gender, or age, to create solutions that meet the dynamic needs of our clients. And currently, there are about 120 of us in the organization with an average age of 35. 70% of us are technologists and 60% are foreign nationals. And currently, we have about 27 different nationalities represented in our organization. We have initiated a partnership with Machine Learning Tokyo, and we are very excited about this partnership. And through this partnership, we hope to contribute to the further development and growth of the technology community. So with that, I would like to give you a very brief introduction to the team that I currently belong to, called the KIT Lab. The KIT Lab is the team that was established in February of this year to constantly monitor information on latest technologies, and we research or apply the next generation technologies to build commercial solutions. So we have our ears open to academic meetings or various initiatives or research that are going on in the various both government and private institutes. And then once we have identified certain technologies that we're interested in, for example, quantum computing, we apply that technology in our domain. So we carry out POCs or build prototypes, or we do benchmarking of the technology, and to see if it's applicable within our business. Then once we have verified that, we pass on the idea or prototype to the technology and solutions department, and they'll create a commercial product that can be used by our clients. So this is our current KIT Lab members. So there are about 9 of us in the team. So Toyota-san here is currently leading the work around surrounding the intelligent agent and the secure computing. Chiba-san is leading the work in knowledge processing, scientific visualization, and edge computing. And I am leading the work in smart transaction pillar. And the work that I present here today is mainly done by myself and also Max here, who is currently a senior researcher as well. So just a quick background about myself. I am originally from the AMO physics background. So as a graduate student, I was working at the Advanced Light Source at Lawrence Berkeley National Lab. And I was carrying out theoretical calculations to understand some of the interesting experiments that were going on at the synchrotron radiation source. And one of the very exciting and interesting studies that I carried out was to demonstrate the experimental theoretical work that we basically demonstrated that the world's smallest double slit experiment was possible using the hydrogen molecule. Once I completed my graduate student degree and moved to Stanford, where I was once again a postdoc researcher or postdoc researcher. And here I carried out the theoretical calculations on the experiments that were being carried out or being planned at the linear coherent light source. And we investigated things like DNA photoprotection mechanisms. And we found out that even though DNA bases can absorb strongly in the UV, they have an interesting way to protect themselves. And that was involved the coupling of electronic and nuclear motion. And currently at KIT, I am leading the initiative around the smart transaction pillar. And one of our work centers on building a real-time audit system. Because of the massive volume and the complexity in the transaction data, it makes a timely audit very challenging. So what we're doing is we're investigating the application of novel technologies such as quantum computing to tackle this problem. So here is kind of the example of the anomaly detection business platform that we aim to build. So we have a data coming in, and then we process that data and we feed it to the quantum classical algorithms. And we're interested in identifying things like round-tripping transaction, network intrusion, or fraud detection. And output of this particular model is given to an auditor. So we have human in the loop. And essentially, at the end of the day, the auditors are going to make the final decision whether or not certain transaction or certain account is illicit. And another advantage of having the person in the loop is that they can give a feedback back to the model to improve the system. So the current development status at KIT. So for the quantum computing, we are concentrating on optimization tasks, and we're carrying out the development using public data. And we also started using some of the client data, but of course, we're not using quantum computer at that point. For the POC, we've done things like supply chain management, anti-money laundering, round-trip transactions, and also intrusion detection system. And then this is kind of the quantum classical computing platform that we envision creating here in the smart transaction pillar. So we build everything on the technology foundation of the cloud. So we are using IBM Q, D-Wave systems, and Fujitsu's digital annealer, as well as the Cloud Next. This is our classic architecture that we're providing as our own service. And then on top of that, we build a technology platform. So we have these types of optimization components, and we also have other classical machine learning components as well. And then using the components of this technology platform, we build business platforms that we provide to our clients. And with that, I would like to now first go into a little bit more detail about the quantum computing effort that we are carrying out here at KPMG Ignition Tokyo. So quantum computing in KPMG, and we are basically aiming towards quantum readiness within this year or the next year. And we strongly believe that another quantum revolution is on the horizon. So quantum physics has brought significant impact in our daily lives, things like lasers and transistors that are in every electronic device, or most of the electronic devices that we use today come from quantum physics. In terms of quantum computing, a significant advancement has been made in the field, and that has a potentially significant impact on various sectors, things like finance, security, energy, logistics, and so on. And some also believe that this will create a multi-billion-dollar industry by 2030. We know that the investments in quantum computing is on the rise, with the US announcing $10 billion investment in AI and quantum computing. China announcing a $70 billion investment in technology, including quantum computing, and also EU announcing the investment of 80 billion euro in the supercomputing that includes quantum computing. So KIT, we are aiming towards quantum readiness, and we hope to do so by gaining a knowledge through first-hand business-driven implementation of the technology, which will allow us to investigate the types of problems to be solved with the technology, and it will allow us to build the framework to transform quantum capabilities into business values once powerful enough quantum computers are commercially available. So the business cases that I would like to talk about today is one is the supply chain management, SCM, and the other one is on the building an anomaly detection system. So starting with the supply chain management, which has a significant impact on the businesses, and it is the integration of key business processes to help organizations gain sustainable competitive advantage by directly influencing its performance and risks. So potential optimization area of our interest are transport optimization, sequence scheduling for both employees and machines. We would also like to see increased traceability, and also another optimization task of interest is an inventory optimization. So for the anomaly detection, and specifically in use for the audit, there are various challenges faced by the organizations due to the massive volume and the complexity of data. It is also a highly regulated environment which requires sophisticated monitoring system. And now audit usually occurs after the fact. And this is because the real-time audit is very difficult, technologically speaking. And a lot of the times, or a lot of the organizations still rely on manual approaches to detect these or to find these type of activities. And these are prone to error. And once we make an error, it hurts the reputation of the organization. So we believe that this is a very important topic for us. The area of interest is the accounting fraud, things like round-trip transactions or intrusion detection or anti-money laundering in this case. Now, I would like to first discuss a little bit detail about the supply chain management issues. And in particularly, we're interested in a transport optimization case or the task currently, which plays a vital role in various stages of the supply chain management by facilitating a smooth flow of materials and goods. And the representative optimization task that I will talk about today is on the traveling salesman problem, which is an archetypical case of combinatorial optimization. And the task here is to find the best or shortest delivery route So let's say you are given a list of locations and the distances between the pairs of locations. This traveling salesman problem asks for the shortest or the best delivery route that visits each of the location once and returns to the origin. To solve this problem in a brute force manner, it takes about n factorial in time complexity. So it's really not feasible for n greater than about 20 cities or so. This problem has also been studied for over a century, so we believe that this is a suitable benchmark because there are a number of heuristic approaches that are efficient to solve this problem. So here we're comparing the approach of quantum annealing versus the classical approach. More specifically, we're using Google's OR tools to make the comparison. So here is the supply chain management business platform that we envision. So we have, once again, the foundation, the cloud, and we have the data layer, and we also have the analysis, optimization, and simulation layer. And we build the components of the technology platform using these type of tools. So we have the data processing tools, and we also have the optimization tools. And these are built from the quantum computers, quantum algorithms, or it could also be a classical one. And a particular interest here, once again, is a traveling salesman problem. And we're also building components to do causal inferences, probabilistic programming, and stochastic optimization using these type of tools to provide the business intelligence. Then now I would like to describe how one could solve a traveling salesman problem using with quantum annealer. Sorry, these equations are kind of a little bit weird. I think it happened while I transferred the file to my personal computer. But then the objective, so to solve this problem, if we using a quantum annealer, you have to first define what's called an objective function, or in physics we call this a Hamiltonian. And this Hamiltonian has two terms, HA and HB, and it is function of an x, and this is a vector. And each element of x is a binary variable, so it could be either 0 or 1. So in the case of 4 cities, so let's say you have cities 0, 1, 2, 3, and if you were to plot out or visualize this x vector, it would look like this. So on the row, it has a city to visit. So it has cities 0, 1, 2, 3. And on the columns, this is the order of the visit. And so let's say if you do an optimization and you find that x11 in this particular case is 1. So in this is the situation. So this means that the salesman travels to the city location 1 on his second visit. So that's what it means. And so what you want to do here is to find the minimum. So let's say h, you were to plot this objective function h as a function of some coordinate q1 and q2. And then you get this type of potential energy surface. And every point on this potential energy surface is a route that the salesman could travel. And the magnitude of this objective function is proportional to the distance of a particular route. So in the hills, the computed route is long, and on the valleys, route is shorter. So the task here is to find the shortest path possible for the salesman, so it will be the global minimum here. And then this is described by this HB contribution or HB term, which is kind of weird, and you cannot kind of distinguish what it says, but that's what HB is for. But then not only you're trying to find the minimum distance for the salesman to travel, he also has to fulfill some constraints. So one of the constraints then there are two constraints that he has to fulfill, and one of them is governed by this term here. And then basically this says that the location appears only once in a route. And then the other constraint is shown here, but which is not clearly shown. But this basically states that you can only visit one location at a time. So by minimizing this type of quantity under these constraints, then you could get a solution like this. This is the optimized route that you could actually get from this task. And here what it says that you start with location 0, goes to 1, goes to 3, goes to 2, and comes back to 0. Now I would like to describe this quantum annealing formulation or approach a little bit more in detail so that you can actually see the advantage of this approach over the classical approach. So once again, the objective is to find the shortest route or the minimum of this objective function or Hamiltonian. And the global minimum is equal to or basically is defined as the shortest distance route. So to do this classically, you pick a point in this potential energy surface, and then you find the downward slope to land at the minimum. But then this valley, you're not sure that you're at the global minimum. So you have to get out of this valley and find another valley. And you have to do this repeatedly until you're confident that you are on the global minimum. So you have to do the search exhaustively. And then this is why, as you increase in number of locations, this type of approach becomes intractable. Quantum annealing actually works quite differently. It starts with a superposition of all locations. So you consider all the locations on this potential energy at once, and then each location has some probability for it being the shortest route. And then you evolve those probability according to the laws of quantum mechanics. So you're solving this time-dependent Schrodinger equation. At every step of the search or every time step that you make, more and more probability will be focused on the valleys over the hills. And so after sufficient time step has been taken, then the optimal route will have the largest weight. So in principle, computational time of this approach stays constant as n approaches, n is increasing, and this is the true advantage that we're hoping to see. So here is the preliminary result of the traveling salesman problem. And the metrics that we use to evaluate our approach is the computational time shown on the left and the quality of solution, in this case, the total distance traveled, and that is plotted on the right. And so on the figure on the left, this is in a log scale, and this is the second. And then we are plotting it as a function of the number of locations. And this is the y-axis here is a total distance traveled in kilometers, and this is number of locations. What's obvious here is that the classical approach, the OR2 shown in red, outperforms the quantum annealing approaches shown above. It has the faster computational time, and it also has a better solution quality. So when you actually concentrate a little bit more on the quality of the solution, Fujitsu's digital annealer shown in green does reasonably well, but then it basically diverges after 25 locations. For the D-Waves hybrid approach, it does reasonably well to about 20 locations, but once again, after that, it diverges. We did the same calculation using the D-Waves pure quantum computer, but then it can only handle about 7 to 8 cities or so, so it's not plotted here. Another thing that I did want to point out is that for the quantum annealing approach, computational time, there's a trade-off between the computational time and the quality of the solution. So when you go back to this, so once again, you're searching for the global minimum, and every time step that you take, more and more probability will be on the value over the hill. But then you have to take a sufficient time step to reach this global minimum. And more complex the terrain becomes, much harder it is to find a global minimum. So as you increase the annealing time, the solution quality does improve. As you can see, this is a Fujitsu's digital annealer, and different circles represent different time steps that has been taken. So here you take about 10,000 time step, here is 50,000 time step, and this is 1 million time steps. And you can see, of course, the computational time does increase, but when you look at the solution quality, this is 10,000, this is 1 million, you can see that the solution does improve quite significantly. Another thing that I do want to point out is that even though the classical approach does seem to be better in this particular case, but then we still believe that there is an advantage for the quantum annealing, and that is in the computational time scaling. For both the Fujitsu's digital annealer and the D-Waves hybrid approach, the computational time stays constant to about 30 cities or so, while the OR shows, OR essentially is the Google's classical approach, shows an exponentially increasing computational time. So we believe that this is very promising, and that if the powerful enough quantum computer is to come out in the future, this trend might reverse. With that, now I would like to move on to another topic, which is anomaly detection. I will try to go through this very quickly. So the two cases that we're interested in is an accounting fraud and anti-money laundering. We're interested in accounting fraud because recently Toshiba's round-tripping transaction incident occurred, and there has been increased pressure from the FSA to crack down on this.
But if this is a challenging task because of the high variety of these type of transaction, presence of falsified data, and a large volume, anti-money laundering, we're interested in it because of the significant societal impact. The monetary impact is said to be about 3% of the global GDP. And the challenges are that the bad actors adapt and they change their tactics. And you also require an insightful full graph network, which some of the banks don't, you may not you have. The approach that we are pushing or we're investigating is a graph learning approach, and we believe that this is a powerful approach to identify anomalies in data. But the disadvantage here is that some of the graph algorithms don't scale well to large graphs. So here the POC is to implement the quantum computers and the quantum algorithms to in this for the graph algorithms to see in the future we will be able to speed up this process. So once again, this is the anomaly detection business platform. Once again, we have the cloud, the foundation on the cloud, and the data layer and graph machine learning layers and so on. Then we build it from the components utilizing the components that are built in the technology platform using these type of libraries. Then this is the kind of the theoretical part of it. So the task of graph partitioning, which we will investigate to compare the quantum and classical approaches, is to partition a set of nodes in the graph into a mutually exclusive groups by minimizing the number of edges that are cut. So once again, this is the objective function or Hamiltonian, and it has two terms, the constraint term and the sum term that you want to minimize. And then x, once again, is a vector whose element is a binary variable. And the constraint here is that you want the number of the nodes in two partitions to be equal. So that's the constraint. And then the things that you want to minimize is the number of edges that are cut in order to make the two partitions. So what you want to do is you want to minimize the number of edges that are cut, and then you want to separate the graph in two partitions of equal size. And then if you are able to do that successfully, then you can actually partition a graph in this time manner. So you have the blue partition and the red partition. There is a way to actually partition a graph into k different partitions in using the quantum annealing approach, but I'm not going to go into the detail here, but it's called a k concurrent graph partitioning. So here is a preliminary result. Once again, we plot the computational time, and now I'm plotting out what's called the graph modularity. And this term graph modularity is essentially something that is inversely proportional to the number of edges that are cut, meaning that the larger the modularity, the better the quality of the solution. So here I'm plotting out the computational time as a function of different number of nodes, once again in the log scale. And then here is a graph modularity as a function of the nodes, and this is the value of modularity. So when you look at the computational time, once again, Metis is a classical approach, does outperform the D-Waves hybrid approach. Once again, it does increase a little bit, most likely an exponential, while the D-Wave stays constant. So once again, we believe that this is a promising result for the D-Wave approach, even though in absolute sense, it takes a little bit longer than the classical approach to solve a problem. But when you look at the modularity, so purple here is the D-Waves result, and the red is a classical approach. What you can see here is that after 1,000 nodes in the graph, actually the D-Wave hybrid outperforms the classical approach. So another thing that I do want to note here is that there is a term called the Lagrange multiplier that plays an important part in this optimization task. So you do have a terms HA and HB in this case, and HA is a constraint that you want the numbers of the number of nodes in two partitions to be equal. And B here, HB is that you want to minimize the number of edges that are cut. And there are coefficients here, A and B, and those terms are important. If you have A bigger than the B, that means you're putting more emphasis on dividing the graph into two equal components. Well, if B is larger than A, then you're putting the emphasis on minimizing the number of edges that are cut, and this plays an important part. So when A is larger than B, in this particular case, Lagrange factor 1, then you actually get this type of curve, and then the performance is not so great. But then if you increase now you say that B is a little bit more important in then A, then you get this curve which outperforms the classical approach. So with that, just a conclusion and outlook. So we believe that there has been a significant advancement made in quantum technology, but quantum devices do not yet provide obvious benefits. But we believe that with increased expectation and investment, quantum revolution is on its way. And we strongly believe that quantum readiness is a key to success for industry organizations. And we can do so by carrying out first-hand experience to gain intimate knowledge of the technology. And through such a work, we can identify type of problems to be solved, or we can understand its limitation as well. The business cases we studied were supply chain management, particularly the traveling salesman problem. And we also looked into how we can speed up the anomaly detection task by speeding up the graph algorithm component. We saw that the quantum annealer does give constant time scaling as a function of problem size. And we strongly believe that with increasing quantum volume, the task of optimization is a promising area for quantum computers. Then finally, quantum computing activities in KPMG Global. So we are definitely not the only ones that are working on this technology and globally. So we do have a global emerging technology community, and one of them is a quantum working group call. So we've done a publication of thought leadership articles and white papers. Various firms, KPMG firms, are initiating discussion with the startups and technology companies, and particularly Denmark is very active in this arena, and they've done the co-creation of first QKD link in Denmark. They're also helping to create national quantum strategy in Denmark. And also the Germany firm is working on cybersecurity and quantum computing, and they're initiating client engagements here as well. So with that, thank you very much for your time.
Thank you so much, Miyabe-san. Can you hear me?
Yeah, I can hear you.
Wonderful. Thank you. This was an absolutely excellent presentation, I think, from both perspectives, from the applied perspective, as well as from the theoretical perspective, considering the fact that quantum computing is something fairly new to our community. So fantastic. Thank you so much. We have a bit of time for some questions, and we do have some questions if you're ready for it.
Sure.
And maybe we'll start with the first one. And you mentioned, in one of your last slides, in your conclusion slides, that maybe, some of the benefits are not yet obvious, but we can already see, speed up and constant time scale and things like that. And someone is asking, where do you see, one of the biggest challenges for industrial applications of quantum computers is that we don't see this and I put this on quotes, killer application yet, right? Or this big problem that can only be solved using a quantum computer. So this is maybe more of an applied question. Where do you see these applications where we would really benefit from using quantum solutions?
Sorry, so you're talking about specific domain of our interest, or are you talking about more of like in how much longer should the hardware side be developed to achieve quantum advantage?
Yeah, maybe more from the application side. So you mentioned the application side, what we've seen today is a lot of finance, right? A lot of problems in finance that can be used with quantum solutions. Do you see specific properties there, specific domains there, or specific applications? What is your take on that?
Let's see. So we believe that we've been investigating what's called a combinatorial optimization problems, and then I still believe that the combinatorial optimization problem is an area that quantum computing can surpass the classical approaches, and just because of the number of states that you have to consider to solve a particular problem like combinatorial optimization. So classical bits, you can only hold information of 0 or 1. And then, if you wanted to hold more and more information, it increases by 2 to the n. The amount of information that you can contain, and where n is number of bits. But then if you were to think about the quantum computers and the qubits now, then it can essentially simultaneously describe the states of 0 and 1.
So essentially, if you were to, let's say, so I think it's just a simple calculation, but okay, let's see if I can do this now. So with 2 qubits of information, you can essentially contain about 4 different combination of states. Then I believe that with about 10 qubits, I think you can hold information that is 1,000 times as greater than the classical ones. And then with about 50 qubits, I believe that it's like gojucho, which is, I think it's 50 trillion or something like that. But basically, as you increase in more and more qubit size, number of states that you can describe, it basically explodes. So I think that combinatorial optimization problem, which can be applied to things like traveling salesman problem, or even like portfolio optimizations and things like that, would definitely be an area that would be the promising area for quantum computing, I believe.
Excellent. Maybe we can move on to the next question. In terms of scalability with quantum computing, did you ever reach a point where the scale of the data points or nodes that classical computing was slower than quantum?
At this point, not yet. And this is because, I mean, quantum computers for a D waves, it has about 5,000 qubits. And if we were to use a pure D waves quantum computer, we could only go up to about 100 nodes or something. So we had to always rely on the quantum classical approaches. So, and then, but Fujitsu has, it's not a quantum computer, but it's a quantum inspired device. And for that, it's an 8,000 qubit machine, but then I think the connection between the qubits work better. So the D-Wave, I think they have this description called a chimera graph, where not every qubit is communicating with other qubits. So that gives the limitation. But then with about 8,000 qubit on the Fujitsu's digital annealer, I think I was able to go up to about 3,000 nodes, but it never got faster than the classical approaches. But the Fujitsu is coming out with something, I think it's 100,000 qubit machine next year or so. So we're kind of excited about that to see if there is that particular point where classical quantum approach is faster than the classical ones.
Very, very exciting. We have a few more questions. Let me see. There was one question. Let's see. Are you using some kind of distributed computing for data processing in real time when you're doing anomaly detection? And if so, what kind of technologies are you using?
At this moment, I believe that we are working towards that, but not at the moment. I know we do have a massive amount of data, and we definitely have to go into that, but that is still work in progress for us.
And so our community is more in the machine learning field. I'm sure you had heard about quantum machine learning, especially in this field. Do you have thoughts on that? Where do you see the future of this field? Is this something that you might be looking into as well?
So I think Google described these two types of data sets. So we have like what's called like, I think classical data sets and then the quantum data sets, I believe. So quantum data sets are essentially a description of quantum mechanics or something like, for example, like molecules. So essentially it's really good at solving things like doing what's called in quantum chemistry, they call it the Hartree-Fock. So essentially calculating the energies of molecules and things like that. But I think when you apply this same type of idea to things like image classifications and things like that, it doesn't work very well. So I believe that, I think there will be the day will come that they can apply it, but I think it's not going to be anytime soon.
Maybe related to this, I remember we had a discussion also with Kit on, what were kind of the major breakthroughs or that supported major breakthroughs for AI. So what kind of happened in AI that allowed AI to be deployed at scale? And it's a lot about, accessibility to data, to GPUs, to acceleration, to computation, as well as to the whole software stack, right? Tooling around machine learning. And all of these things really helped push AI in the past decades, 1 or 2 decades, to be applied and to be and to see the progress, not only in research but also in industry. What do you think is needed in the quantum computing field? What are the main challenges so far in terms of maybe hardware, and where do you see what needs to be done in the future? How long may it take? What are the main challenges for deploying quantum solutions?
So I think there are several, I think, aspects. I'm not a hardware guy, and I don't exactly know how people make quantum computers, but definitely increasing in quantum volume is the very difficult and challenging task. But I think IBM and Google and everybody is doing very well in this sense, where they are planning to double or even quadruple the quantum volume every year. And then I think IBM is planning to release like 1,000 qubit machine. Currently it's at 50. I think next year or the year after, I can't remember when exactly it was. So I think with that type of investment and work surrounding the hardware side, I think it's very promising. But I think another thing is that so a lot of the things that all of the things that I presented today is solved by what's called a quantum annealer, and then there's another quantum machine called quantum gate machines, and I think a lot of companies are placing their bet on that technology because it is a little bit more general, and you can so for the quantum annealer, it's really good at solving like combinatorial optimization and something that can be described within the framework of what's called the annealing process. But the general purpose quantum computer essentially should be able to do more than just an optimization task. So I think things like quantum machine learning and all that stuff will fit into that quantum gate category rather than quantum annealers, I believe. And then for that, I think the challenge really is that now it's very difficult to, or from my understanding, it's very difficult to code for the gated machine because you really have to control the spins of each of the qubits. So you have to control it with the different gates and so on. And then, not all the gates are available yet. So kind of there's a barrier, like you have to really understand mathematics and how you control the spin to design software and things like that. And I think once you kind of have more developers that kind of put all those things under the hood, and then so that they can focus more on the application of these devices, then I think things will start to pick up more. But I think there is just what they call a big barrier for just anybody to pick up quantum computing and develop solutions.
On that note, or on a similar note, very interesting what's happening also to see the quantum computing community as well as the open source initiatives that are happening in the field. I remember last year we had also a talk on open source quantum computing tools. So this is definitely going to push in that direction and to help make it more accessible, probably, and push in the right direction. Right. Absolutely fascinating. I think we're almost out of time, but I would really like to thank you, Miyabe-san, for this really great talk and the great insights that you gave us today on quantum computing, both maybe the theoretical and the applied side. From an MLT perspective, we are very, very excited about this partnership we have with KPMG Ignition Tokyo. I think it's really great to have a strong partner that also supports the ecosystem and community. And we'd love to do this again in the future with KIT. So one more time, thank you so much, Miyabe-san. A virtual applause to our speaker today. If you guys have more questions, please drop them in on Slack or join us on Slack. We will do a lot more of these talks. I hope you enjoyed today's quantum talk with Shungo Miyabe-san from KIT. Virtual applause from everyone. Again, thank you so much, and I'll talk to you and I'll see you soon.
Thank you so much.